Okay, welcome back to Greenplum Summit 2020, the Reimagined Digital Customer Conference. My name is Jacques Eistock, and my next guest is Ekta Khanna. Ekta is a senior member of our technical staff in R&D, and she's going to go talk about GPUs, which you heard a little bit from Michael, analytics, and Greenplum. So Ekta, over to you.
Hello, everyone. I'm Ekta, and I work with the advanced analytics team for Greenplum. And we'll be talking about training deep neural networks in parallel with GPUs on Greenplum database. So this is the agenda that I would like to cover today. First, we'll give you an overview of what Tanzu Greenplum with GPU acceleration is all about. Then we'll talk about how we can use it to train multiple models in parallel. We'll go through some examples showing the performance on Greenplum and upcoming features for automated machine learning. So to start with Tanzu Greenplum with GPU acceleration, next slide. Here we have some examples of deep neural networks. The MLP or multi-layer precipiton is a general purpose fully connected neural network that is used probably, I would say, for smaller problems these days because there are several custom types of networks which we have built today, like the RNN or the recurrent neural network, which works good on a problem associated with sequential data like speech recognition and machine translation. Then we have the convolutional neural network, the CNN, which is a class of neural network mainly used for computer vision and image processing. It can be used in applications like image recognition in your smartphones or employee identification in a lobby, or maybe reading license plate numbers across the Golden Gate Bridge. So how deep learning algorithms usually work is that there is a data set on which we want to train a neural network that we just talked about in these examples and create a model out of it. And once we have the trained model, we want to use it for inference or prediction. The majority of the effort that is spent is on training this model itself. So for that, we have GPUs. Moving to the next slide. GPUs are graphics process units. These are basically good at performing a lot of simple computations in parallel, such as matrix operations on large data set, which is mainly a key aspect of the deep learning algorithms itself. They also have a high memory bandwidth that makes them well suited for training deep learning algorithms and can be virtualized too. But as we heard, they are expensive. Moving to the next slide. Training neural networks or deep learning neural networks can be challenging because the model accuracy is basically a function of the model architecture itself and the hyperparameters, which are the tuned parameters for the model. So even experienced data scientists who have many years of experience a priori do not necessarily know what model architecture will work and what associated hyperparameters for that model architecture will work for them. So we need to try, and we are trial and error method. We come up with a good model. To give you some more context on the complexity, this is an example where we want to train 4 architectures like a 3-layer CNN or a 5-layer CNN on 4 batch sizes. We want to test like 4 different learning rates. The learning rate here is basically the rate at which the gradient's descent will crawl down the curve. And we want to probably test like 4 different regularization or relaxation methods. So we are left with almost like 256 different configurations, and we want to speed this up. So for that, we need parallelism and GPUs. Next slide. So what we came up with was to take the power of MPP in Greenplum and combine it with the power of GPUs. As there is a lot of research going on in deep learning algorithms, and we have libraries like Keras and TensorFlow. So instead of building the training algorithms from scratch itself, what we did was we integrated these deep learning libraries to work with an MPP database. And since GPUs are expensive, so for cost purposes, our customers can have GPUs attached to fewer segments for training deep learning neural networks. And accordingly, the data set would be distributed on those GPU related segments. Next slide. Training multiple models in parallel. So we have been talking about how complex or time intensive training multiple models can be. And using the MVP capabilities of Greenplum, we can parallelize this process. So now we'll be talking about how we achieve that parallelism. Next slide. As Jock already mentioned, Apache MADLib is an open source in-database machine learning library that can be installed on top of Greenplum or Postgres. And as part of MADLib, we have this implementation of learning multiple models at the same time, which is known as the model hopper parallelism. And we'll see what it is in the next slide. So what is model hopper parallelism? Suppose we have P workers, 3 segments in this case, and we want to train S configuration on these 3 segments. We start in a round robin fashion, selecting 3 model configurations that we want to train. And once the model is trained on all the rows in that segment, it is hopped to the next segment. And we do this until each model has been trained on the entire data set. To go through some terminology, training the model on all rows of a segment is known as one sub-epoch, and training the model on all segments is known as an iteration. One more thing to note here is that the accuracy of the model that are being trained is mainly depends on the gradient descent, which is actually robust to the visit order. So it doesn't really matter how the model is hopped as long as each model sees the entire data set. Next slide. These are some of the APIs that are there for loading the data for deep learning. Defining the model configuration, which gives a model selection table with all the different configurations that we have, and training the model itself on the data set, which gives the trained models as an output. Next slide. So now we'll talk about some of the examples and performance that we saw with Greenplum. Next slide. So we trained a deep learning network on vSphere on a subset of places 365 with a training set of 500K color images with 100 labels and a validation set of 100 images per category. That's almost like 10K images. So we trained it with the VGG16 CNN model, which has almost 133 million weights in the model. And we trained for 12 different set of hyperparameters and optimizer and learning rates. Next slide. So what we saw was it took almost 2 hours per iteration for each iteration, which would scale with adding more nodes. And the inference using the model that we trained was pretty accurate to the actual image that we see here. Next slide. So this graph basically shows an overall GPU utilization of our experiments. It is for 1 VM, which is like 3 virtual GPUs, which are 3 virtual GPUs. The drops in the curve that you see is due to the hops that we spoke between each sub-epoch. And if you look at the graph, we see that almost up to 80% GPU utilization was achieved during sub-epochs, and overall we had like around 67% GPU utilization, which is due to the hops that we see. We are trying to reduce these gaps, and yeah, let's see. Next slide, please. So we also tested the deep learning module on Purple Cloud for RSNA pneumonia detection set, which has around 26,500 colors images with 227 to 27 image size, which were downsized. And then we trained it using AlexNet, which has almost 60 million parameters, and we trained for 30 different model configurations. With these 30 model configurations, what we saw on a single host, it took 39 hours versus 8 hours when using Greenplum with 5 hosts. That's almost 5x faster. Next slide. Automated machine learning. So for data scientists, training multiple models is mainly a way to efficiently select the best model architecture and hyperparameters. Now that we have seen how efficient training multiple models in parallel can be on Greenplum, but currently there's no good way to tune the hyperparameters for selecting the best model. Next slide. So to ease this process, as part of MATLAB 1.18, we are introducing hyperparameter optimization. The two most widely used strategies for hyperparameter optimization is grid search and random search. And as the name suggests, grid search is a brute force algorithm that evaluates all the configurations in a discrete search space. But this can be extremely slow in high dimensional spaces. And on the other hand, random search, which randomly samples configurations to evaluate and can work in discrete and continuous spaces. So what we've seen is that random search has proven to find as good or better models within the fraction of the resources as the grid search. But this can still be resource heavy for complex architectures in big search spaces and big data. Moving to the next slide. So for faster model selection, we looked at the AutoML algorithms like Hyperpan that speeds up random search with adaptive resource allocations and successive halving. So what it does, it mainly takes two inputs, R, which is the maximum amount of resources that can be allocated to a single configuration, and eta, which is the number of configurations that are discarded in each round of successive halving, also known as a bracket. So how it works is that it starts with the most expensive bracket to explore the maximum configurations. And with each iteration I, it keeps the top 1/eta configurations and prunes the rest, as shown in the graph below. Finally, at the end, what is left is the final bracket, which has the top n configurations. The initial experiments have shown that Hyperband speeds up random search by up to 70%. So how do we implement Hyperband in a distributed environment like Greenplum? So if you look at the table below, to utilize the resources most efficiently, we use model hopper parallelism. And what we do is we plan to allocate the iterations of the brackets diagonally. That is, instead of running the bracket sequentially, we want to start with the first iteration of the next bracket as soon as we start with the next iteration of the first bracket. So at any point in time, we will have all the workers that are in use. So to summarize, I would say training deep learning neural networks is all about scale, and VMware Tanzu Greenplum can run GPU accelerated deep learning workloads at scale. Thank you. If you have any questions, you can reach out to me at the email.
It's very exciting, actually, to see how we both can leverage the power of GPUs with Greenplum, as well as how we've methodically thought through the process of taking these models at scale and being able to leverage all of the infrastructure resources that are available to us with all of that data. So thanks again.